Extreme physics. And the secret question for today is...
A cannonball is launched at a 30-degree angle above the horizontal from the edge of a cliff 20 meters high. If the speed of the projectile is 40 meters per second, what is the greatest height above the cliff that the ball achieves? How far from the base of the cliff does the ball land?
All right. So we have a basic projectile motion problem. Let's draw a picture. So we have, of course, we have a cliff. It wouldn't be a projectile motion problem without a cliff. Let's see. Hopefully that's drawn big enough so that you can see. We're going to launch a cannonball off there. I'm just going to draw the ball. I'm not even going to draw... Well, I guess I could draw the cannon. Here's a cannon. It's a little cannon, and the ball goes off at some speed. What was the speed? 40 meters per second. So it goes off at 40 meters per second at an angle of 30 degrees. And then it's going to, of course, that's its initial velocity. Here's its trajectory. It's going to do something like that. And it's going to hit the ground, travel in a nice parabola. It starts at position 0. We're going to want to know the maximum height that occurs right there. We'll call that position 1. And we want to know something about where it lands. We'll call that position 2. And the height of the beginning of this thing is 20 meters, I believe. Let's see. Yes, 20 meters. All right. So, of course, the first thing we're going to need to do is break the velocity vector into its vertical and horizontal components. So let's do that right here. So the thing is going at 40 meters per second like that. Let's calculate Vx, which is going to be the total velocity times 30 degrees. Total velocity times the cosine of theta. And in the y direction, we have the opposite side of a right triangle. So it's going to be the total velocity times the sine of theta. Those are going to be the components of our velocity. So we have 40 meters per second times the cosine of 30 degrees. And this is 40 meters per second times the sine of 30 degrees. And I know that that is, we'll give it 3 significant figures, 20 meters per second. And this one is going to be 34.6 meters per second in the x direction. So it's going faster horizontally than vertically. And that makes sense because it's 45 would be equally, but this is more horizontal. So, all right. So as in all these problems, we're going to need to break this into its vertical and horizontal components. All right, keep them separate. It's important to do that. What happens in the x direction stays in the x direction. Velocity initial, which is the velocity final in the x direction, it is constant because there are no horizontal forces. I hope I'm not getting too much glare. Equals 34.6 meters per second. And in the y direction, v initial, this does change immediately. Immediately, it's accelerating, is 20 meters per second. Of course, like I said, it's accelerating downward at negative 9.81 meters per second squared. That's a positive velocity because it's upward. To solve the first problem, we want to know how high it went. So at that point, V1, I'll call this V0. I should call this V0. I just call it V because it doesn't change. V0 in the y direction is 20 meters per second. V1 is 0. All right. V1 is 0, and we want to know what really what the y1 position is. But I'll just call it D because that's what it is, the displacement. That's what it is in our equations. So I'll call it D. All right. So D in the y direction. It looks like we can use a squarey. It looks like squarey. V1 squared equals equals v0 squared plus 2 times the acceleration times the displacement. Let's calculate the displacement. Displacement equals v1 squared minus v0 squared all over 2 times the acceleration. 0 squared minus 20 meters per second squared divided by 2 times negative 9.81 meters per second squared. 20.4 meters. 20.4 meters. And I'm getting a positive value. And I guess that makes sense, doesn't it? 20 meters per second. After 1 second, since it slows down at about 10 meters per second per second. After 1 second, it's going 10 meters per second. After 2 seconds, it's going 0. So in 2 seconds, at an average speed of 10 meters per second, 20 meters. Yes, that seems reasonable. So that's the answer for part A. The height above the cannon, this height, right here, from here to here, is 20.4 meters. All right. Let's take a look at the second question. We still need the initial velocity and the acceleration, but now we're dealing with position 2, so we don't need any information about position 1 anymore. We can get rid of this too. We don't need that. We're not going to use that at all. All right. So we want to know how far it goes in the x direction. So we're going to use the y direction to figure out how long does it take to get to the bottom, because the time in the air is determined by the y direction. Let's take a look. We want to know time. What else do we know? We know the displacement. The displacement from here to here is negative, and it's got to be negative, 20 meters. If that's 0, it's down 20 meters. So the displacement is going to be 20 meters in the y direction, and we want to know the time. All right. Now, if you use one of those fancy graphing calculators, you could solve the quadratic. You could use El Grande, d equals VIT plus 1/2 AT squared, and solve for t. You have a quadratic, and V initial or V0 is not 0, so you have to deal with both of these. I'm not going to do that, because solving a quadratic is kind of a pain. I'm just using a scientific calculator, so I'm going to do it as 2 steps, but you certainly could do it using solving that quadratic. Let's do it using 2 steps, using squarey to find the speed when it gets to the bottom, and then we'll use the definition of acceleration to find the time. So I'll use squarey. That's v2 squared equals v0 squared plus 2 times the acceleration times the displacement. And let's solve for the speed at the bottom. So the speed at the bottom is the square root of v0 squared plus 2 times the acceleration times the displacement. And that equals, let's see, hopefully I can fit this in, 20 meters per second squared plus 2 times negative 9.81 meters per second squared times negative 20 meters. Yes, I fit it in. It's all in. All right. Very, very happy about that. 20 squared. And what did I get? I have 28.1 meters per second. Let's see, does that make sense? Well, it's going to be going 20 meters per second when it gets here, and it's got to drop another 20 meters. So, yeah, that seems like a reasonable number. All right, so I got the same number. So nothing could have possibly gone wrong. All right. All right, so that is velocity at 2 in the y direction. All right, so now I can just use this equation. V2 equals V0 plus acceleration times time. Therefore, time equals V2 minus V0 over the acceleration. 20, oh, but I have to be careful here. I almost made a big mistake. This answer, of course, is plus or minus from a mathematical standpoint, but we need to understand that that is downwards, so that's negative. Almost made a big mistake. Anyways, V2, negative 28.1 meters per second minus 20 meters per second divided by negative 9.81 meters per second squared. Our numerator's negative, our denominator's negative. We're going to have a positive time, and I like positive time. 4.9 seconds. 4.90 seconds. Let's see, is that reasonable? Well, it took 2 seconds to get up there because it was 20 meters per second. It loses 10 meters a second per second. So it takes 2 seconds to get up, 2 seconds to get back to here. So that's 4 seconds, but it's going pretty fast. So maybe it takes 0.9 to go the rest of the way. That seems reasonable. It doesn't mean it's right, but it seems reasonable. All right, so the only thing that can go to the other side, the only thing that the XY share are time, actually. So t equals 4.90 seconds. And if I want to know the distance, I'm going to do that right down here. So the distance traveled is velocity times time, average velocity times time, but in the x direction, the velocity is constant. So that's going to be 34.6 meters per second times 4.9 seconds equals 169.7 meters. And that's probably too many digits, so let's give an answer of, the displacement at 2 in the x direction is 170 meters. 170 meters. Okay, common mistake I saw in this problem was that for time, people calculated the time to get up to the top, and they doubled it, and that would only get you to that position. That would not get you to position 2. Anyways, that was the secret problem for today. See you next time.
Extreme Treasure.